we have been looking at basic iterative methods. In iterative methods, we do not solve Ax equal to b directly, rather we solve repeatedly the equation Qxk equal to q minus a xk minus 1 plus b and approach the solution asymptotically. This is what we have seen, and in one of the basic iterative methods, the Jacobi method, we write the iterative scheme as xk equal to q inverse q minus xk minus 1 plus b, which can also be put in this form, finally in the form of mxk minus 1 plus n. In the Gauss-Seidel method, we write the iterative scheme as xk equal to q inverse of q minus a xk minus 1 plus b equal to in this form, which looks exactly the same except the definition of q. In the case of Jacobi method, q is just the diagonal elements of A, and in the case of Gauss-Seidel method, it is the diagonal elements and the elements which are lower than the diagonal method, those constitute the q. So in both these methods, it looks like we have to do inverse of q and then we have to multiply by q. So it looks like a complicated matrix procedures are there, but it is not really necessary to do it that way. We do not do matrix inversion in actual computations, but solve directly in the following way. Okay. So let us consider the set of equations given by a11 u1 plus a12 u2 up to a1 n un equal to c1 and so on here. This u should have been x. So similarly, the second equation is given by a new set of coefficients a21 u1, a22 u2. So the same variables but new coefficients. Similarly, for the nth equation, new coefficients but the same variables. So this is a system of linear algebraic equations. In the Jacobi method, we make use of the first equation and put all these other elements to the right hand side, and so we can put this as a11 x1 k plus 1 equal to a12 x2 k minus a13 x3 k and so on plus b1. So essentially we have this b is the same as the c here. So we have rewritten the original equation that we have here with the same b as what we have for the given equation, and all the other elements except the first element in the first equation is shifted to the right hand side. And so from this we can get x1 k plus 1 as a12 divided by a11 times x2 k minus a13 divided by a11 x3 k and so on plus b1 by a11. So that means all the right hand side is computed and you divide by a11 to get x1 k plus 1. So there is no inversion as such in this. Similarly, the second equation here is written in such a way that only this term is kept on the left hand side, all the other terms are taken to the right hand side. So you have b2 minus a21 x1 and minus a23 x3 minus a2 n minus 1 xn minus 1 minus a2n xn k like this. And if you consider the last equation here, the last equation this term here, this is the n minus x n minus 1 is the diagonal element. So this is kept here, and all the other terms are taken to the right hand side along with the right hand side coefficient here. So in each case, by rewriting it like this, we can evaluate x1 k plus 1 by doing all these multiplications with the previous values of x and then subtracting from b1 here and dividing the result by a11 to get x1. Similarly for x2 and similarly for x1. So you solve each of these equations for x1, x2, x3, xn minus 1, xn. So we start with the initial guess x2, x3, x up to xn, the 0 indicating the initial guess, and solve n equations of equation 2 for x1, x2, x3, x1, x4 all the way up to xn for the first step. And now you have x1 for all of these, and then you again substitute them here and then again solve equation 2 for x1, x2, x3, x all the way up to xn for at the end of the second iteration step. And once you get x2, you can again get all of x3 and so on. So in each case you are not exactly solving this equation, you are using the first equation to get a new estimate for x1, knowing the values of all the other variables from the previous iteration. And similarly, the second equation is used to get the value of updated value of x2, making use of all the previous values of this, and then we can go on. So what we see from here is that it would take n minus 1 multiplications. For example, you have one multiplication, second multiplication, third multiplication, up to n minus 1 multiplications, okay, this and this. So there are n minus 1 because this will make it the nth one. Since it is on this side, we have n minus 1 multiplications to give us this whole thing, and then n minus 1 additions plus this, so n additions, and the whole result of this n minus 1 multiplications and n additions is divided by a11 to give us x1 k plus 1. So that means that you need n minus 1 multiplications and 1 division to solve one equation, and in each iterative step you have to solve n such equations, because you have to get an updated value for x1 and then updated value for x2 and all the way up to xn. So that means that if you need to go from step k to step k plus 1, you need to use a total of n multiplications or division for one equation, and you have n such equations. So that means that there are n square number of multiplications or divisions that are needed to go from step k to step k plus 1. Okay. This is in the general case, and n square does not seem to be such a good thing. But if A is sparse, which is what we have in CFD generated compact grid discretizations, and has only 5 non-zero coefficients for a 2D problem, or 7 non-zero coefficients in a 3D problem, for example with central differencing, then what we have is that in each of these equations only there are 7 non-zero coefficients. So that means that one of these is kept on this side, the other 6 are coming on to this. So that means that you have to multiply only 6 times, not n times or n minus 1 times. Okay. So similarly this is again 6 times. So each equation is going to have 6 multiplications and 1 division, 7. So that is only 7n number of multiplications are needed to advance from k to k plus 1. So in that sense the Jacobi method takes advantage of the sparsity of matrix A. Instead of doing it for all of them, it does only for those equations which do not have non-zero coefficients, and by doing that it goes from n square number of multiplications or divisions to 7n or 5n number of multiplications or divisions to go from step k to step k plus 1. Okay. Now what does that mean? If you have 10,000 equations, 10,000 grid points, then if you do for every one of these, in the general case it would take 10,000 square, so that is 10 to the power 8 of multiplications to go from k to k plus 1. But if the same set of equations is such that A is coming from the usually discretized CFD type of equation, then we have to do only 70,000 arithmetic operations, not 10 to the power 8, which is 100 million. So that is a kind of advantage that we get when you are dealing with sparse matrix, and a sparse matrix advantage is achieved, is exploited by the Jacobi method. So in that sense it makes it much better than in the general case. So in the general case we are not gaining much of an advantage, whereas in this case we are gaining a significant advantage, because this n square looks attractive compared to the n cube by 3 for a Gaussian elimination, but we do not get a solution in one step of k to k plus 1, we have to do many of those. So, how many of those will tell us the total number of computation, and we will see that shortly. But the way that we actually implement Jacobi method is such that we take advantage of the non-zero coefficients and the sparsity of matrix A, and we go from step k to step k plus 1 in 7n or 5n number of or some constant times n, where the constant is of the order of 10 number of multiplications and divisions to go from step k to step k plus 1. And when you look at what is actually required to do these things, it is pretty straightforward. There is nothing difficult at all in going from step k to step k plus 1. It is very simple to program. Okay. Now, what happens in Gauss-Seidel method? For the same set of equations in the Gauss-Seidel method, we have q becoming d minus e and all that kind of thing. Okay. We can now forget all that, and we can rewrite it in this simple form, which results in the same form as what we have earlier. So, that is, the first equation remains the same as in Jacobi method. A11 x1 k plus 1 is b1 minus a12 x2 k minus a13 x3 k and so on up to minus a1n minus 1 xn minus 1 k minus a1n xn k. The second equation is similar to the previous one, except that by the time we have come to solving the second equation, we have already solved the first equation. So, we know the k plus 1th iterative value, the updated value of x1. So, we make use of the updated value here, and we have not solved the third equation. So, we still have only the old value, and then all these things are old values, and then you have b2. By the time we come to the n minus 1th variable xn minus 1 xn minus 1, we have solved for x1, x2, x3 all the way to xn minus 2. For all those things, we make use of the updated values, and only for the yet to be updated value xn k is put as the old value. So, in that sense, the Jacobi method and the Gauss-Seidel method are very similar, except in the case of Gauss-Seidel method, wherever we have an updated value, we substitute that into this, and otherwise it is the same approach, no matrix inversion, and we solve again with an initial guess, and then from this we solve for x1 and then x2, x3 and so on. And again, if A is sparse, we do not have to do it for all of these, and we have only 5 or 7n number of non-zero coefficients, then it takes only 5n or 7n multiplications. So, that means that we are really taking in the advantage of sparsity here and the Gauss-Seidel method will consume exactly the same number of arithmetic operations as the Jacobi method to advance from step k to step k plus 1. But there is one key difference which sometimes makes the Jacobi method better than the Gauss-Seidel method. Okay. One would immediately see the contrast between the two is that we are making use of updated value as soon as it becomes available in the Gauss-Seidel method. So, one would intuitively feel that Gauss-Seidel method should be better than the Jacobi method, okay, which is true in some cases, in many cases where we apply this, but there is one advantage of the Jacobi method as opposed to Gauss-Seidel method, even though it is slower. And the thing is that if you have, for example, 1,000,000 equations and you want to solve these things, then you can solve each equation independently, whereas if you are doing it using the Gauss-Seidel method, if you want to solve this equation, you have to wait for this equation to be solved. And similarly, if you want to solve this equation, you have to wait for all these subsequent equations to be solved so that you can put the updated value. So, that means that if you are making use of large number of parallel computers, and then out of the 1,000,000 equations or 100,000,000 equations, you give to this computer the first 1,000,000 equations, and for this you get you give the second 1,000,000 equation, third 1,000,000 equation, so on. Then this computer cannot operate, cannot start the process until this computer has finished all its computations and given it to you. but if it is a Jacobi method, you can subcontract part of the work to this set of computer, and you can subcontract another thing, and then you can get back the solution from these subcontract computers and then put together and move on to the next one. So that kind of parallel processing is more readily implementable in the case of Jacobi method, because each equation, each set of equations can be solved independently from the previous known values, whereas in this case you cannot solve this equation until all these things are solved, and you need to have these things solved and the information should be supplied to you. So there is the information evaluated by solving the equation and then stored and retrieved, sent back, stored and retrieved. All those kind of operations will become necessary in the more of them will be necessary in the case of Gauss-Seidel method. So that is a disadvantage that is there, but precisely because you are making use of the updated information, you would assume you would expect the Gauss-Seidel method to work, but in some special cases that may be a disadvantage. Okay. So let us come back to this thing here. The number of multiplications or divisions to go from step k to k plus 1 is the same in both Jacobi method and Gauss-Seidel method. The actual number of arithmetic operations depends on how many times we have to solve equation 2 or 3 for the Jacobi method and Gauss-Seidel method to get a converged solution. Okay. So this is, as pointed out earlier, we need 5n or 7n number of arithmetic operations, multiplications or divisions to go from step k to k plus 1. That is only one step. How many steps are needed to get a converged solution? Converged solution here we are saying is a solution in which x k plus 1, that is the updated one, is almost equal to x k, the one that we have updated. If the amount of updating between the previous and the current one is very little, is very small, then you can say it is almost converged solution, because any further updating is not making bunch of change. So if you want to go up to that, how many steps do you have to take to get down to that position? That depends on, that tells us, because in each step you are using 7n number of computations. So that will tell us the overall amount, and how to get that is something that we will have to see by looking at what is this, what is the convergence rate, what are the convergence characteristics. So here we have a very simple problem, a 3 by 3 problem, and x1 plus 2x2 minus 2x3 equal to minus 1, and x1 plus x2 plus x3 equal to 6, 2x1 plus 2x2 plus x3 equal to 9, and we would like to solve this equation using Jacobi method and Gauss-Seidel method, and we would like to solve this with all the values to be 0 here. So what I plotted is iteration number and the 3 values, what are the values that we are predicting and how we are updating here. Since we have 3, we can just show graphically like this, and the computed value of xi is plotted on the y axis and the iteration number is plotted on the x axis. x1 is given in the blue color, x2 is in that reddish color, and x3 is in the green color, each with its own symbol, diamond, square and triangle respectively. And you can see that we start with 0 values for all the 3, and at the end of the first iteration, first step, x1 has decreased to something like minus 1.5, x2 has increased and x3 has increased, and at the next step x1 has increased from minus value to positive value and the other 2 have come down, and at the next step again x2 has come down here, and x1 has come down and x3 and x2 have come up, and after that there is very little change. Okay. So that means that you can see that there is a big change and a big change, smaller change, and then very small changes, and it seems to have converged, because here at least graphically we are not seeing significant change between the previous one and this one. For the same equations, for the same initial guess, if we use the Gauss-Seidel method for this particular case, we were expecting to get much faster solution because of updating, and we see that we have a problem here, because the computed values, the solution finally we can see is x2 is 1, x2 is 2 and x1 is 1 and x3 is 3. So, x1 plus x2 plus x3, 1 plus 2 plus 3 is 6, again 1 plus 2x2 that is 4 minus 6. So, that is 1 plus 4 minus 6, that is minus 1, so on. So, the true solution is 1, 2 and 3 for x1, x2, x3, that we have got in very small number of steps here for the Jacobi method. But we see that with the Gauss-Seidel method at the end of 4 iterations, the values are coming as something like in excess of 200 for x2 and then in excess of minus 200 for x1, and x3 is also not a small quantity. And at the next step here, x1 has become minus 600 and x2 has become plus 600, x3 has become minus 50 or something like that. So, instead of being converging to values of 1, 2, 3, they are diverging. And so, in this particular case we see that Jacobi converges quickly and Gauss-Seidel method diverges. Okay. We can also have other system of equations in which Jacobi method diverges and Gauss-Seidel method converges, and some others in which both converge and some others in which both diverge. So, any kind of thing is possible, and the difference is the small changes that we are making, whether to update or not update is not something that we can say that updating is universally good, and we cannot say that okay, this is very easy and then let us go and do it, and we can see that there are methods, there are problems, simple problems in which they do not work. Okay. So, it is precisely for this reason we have to do a proper convergence analysis. Just like in module 3, we took a simple problem and we showed that the wave equation and for the diffusion equation, unsteady diffusion equation, we have using the simplistic finite difference approximations can give us sometimes to problematic solutions, and we see exactly the same kind of thing here. And although the iterative methods, these basic iterative methods are quite easy to implement and program, they will not work in all cases. We have to do an a priori convergence analysis to see that the method would actually converge. Only when it converges we can attempt this. So, first thing that needs to be done is under what conditions will a given method converge, and then if it converges, then we are interested in the rate of convergence. Okay. So, this is what we are going to do in the second part of this module 5. So, what we have learnt in the first part are very basic direct methods and iterative methods for the solution of Ax equal to b type of things. We have seen focused specifically on the Gaussian elimination method, the LU decomposition method and the tridiagonal method as direct methods, and we made the point that Gaussian elimination is the most efficient method for a general purpose Ax equal to b, where A does not exhibit any special properties and it is a full matrix or nearly full matrix. And LU decomposition is a specialized method which is almost as good as Gaussian elimination, but slightly inferior, because we have to do two substitution process, one forward substitution, one backward substitution, whereas in the case of Gaussian elimination we have to do only one backward substitution. So, there is a small difference there, but in cases where we have to solve Ax equal to b several times with the same A, then if you do the decomposition of A into L times U once, then that can be used for all the other equations in which B is changing. So, in that sense LU decomposition is becomes a better method than Gaussian elimination. It has other things also that we will see later on. The tridiagonal method is a special method which works very well, but it has limitations in its applicability. It is much better in terms of computational arithmetic operations than either Gaussian elimination or LU decomposition, but it will work only for matrices, A matrix having only 3 adjacent diagonals including the main diagonal, okay, one main diagonal and the one above and the one below. So, only for this case will it work, and even in this case we require diagonal dominance. So, in such a case we do not have any problem, and division with by zeros problem will not arise, and we can make use of the tridiagonal method. It cannot be used for 2D problem and it cannot be used for 3D problem without any modifications. Okay. So, when you come to the iterative methods, we have seen today also in this lecture also we have seen the Jacobi method and the Gauss-Seidel method, and we have seen how easy these are to implement and to write programs compared to the direct methods, where you have to do quite a bit of eliminations and all that, which we have not really gone into. Okay. To write a program for Gaussian elimination will take lot more effort than for Gauss-Seidel method or Jacobi method, but for simple 3 by 3 that we have seen in this class here, we can see that the method is not, any method is not converging, and we also made the point that this is only a special case, and there are methods where Jacobi method will not converge and Gauss-Seidel method will converge and all that. So, we need to do a convergence analysis, and based on this we come up with some criteria for the condition of convergence, and then we look at, once we are assured of convergence, we look at the rate of convergence, and we look in the second part of this module at some special methods which improve the rate of convergence over what can be obtained by the Jacobi and Gauss-Seidel methods for conditions in which they converge. Okay. So, that will be part of the second module, and we will be looking at advanced methods which make use of the iterative approach, and they also make use of some special characteristics of the direct methods, and we will also finally look at the multi-grid approach, which is probably the best general purpose method for sparse matrices that we can coming out of CFD type of problems. So, that is all there in the second part of module 5. So, as of this lecture we can say that the first module is complete. Okay, thank you.